For this video, we're in my kitchen, which is immediately adjacent to the dining room in which I made the first video. The kitchen has some more outlets in it, and I'll show you. Okay, so let's start over here. Here's the dining room. There is outlet number 3 that I talked about in the first video. We'll go to that in a moment. And here is one of the outlets in the kitchen. And there's another outlet in the kitchen. And there are a bunch of outlets, including those two, at the kitchen counter. So let's start where we were last time. In the dining room, this was outlet number 3. And we see that if I'm going to use a long extension cord here instead of a power bar, just because I'm going to be running between outlets. So I can turn on my voltmeter, same as before, and I can see that we have 121.4 volts. And as before, if I plug in the heater, it drops to 116.5. So 121.3, 116.5. So let's suppose, instead of looking at the power or the voltage on that, we go into the kitchen. I'm going to plug in my voltmeter to this outlet, and you'll see that I have 120.6 volts. I'll just quickly run back and plug it into the other one again, 120.5, 120.6. If I go back to the original, if I go back and turn off the power, it rises to 121.3. So there is a voltage drop in this outlet. The voltage drop is less than for any of the other outlets I noticed in the dining room. Let's continue our quest to look at different outlets before I start explaining the theory behind this. Okay, I turned the heater on. Let's go over here. Here we see 122.0 volts. That's higher than the no load voltage on the first circuit. I'll go turn off the heater and we'll check it again. $121.7. Make sure it's not a fluke. $122.1. So we see that the voltage of this outlet goes up by about half a volt when we plug in the heater, whereas the other outlet on the kitchen wall, we saw a voltage drop. So again, I'm not going to speculate. This is a teaser at the moment. Why does the voltage go up here and down at that outlet? Let me show you the results of one more experiment. Suppose I plug my heater in here. I see the voltage drops to 108.4 from what it was, which was 121.6. So more than 10 volts. If I run over to my other outlet, I'll just run over there and plug this in. I'll leave the meter here. I'm now plugged into the other outlet in the kitchen. Now I can play with the heater and see the effect directly. Okay. With the heater running, we see 121.8. And with the heater off, we see 121.4. Heater on, 121.8. Heater off, 121.4. So we're observing the same phenomenon, that when I turn on this heater, the voltage in that other outlet goes up. Happens the other way around too. If I plug it in the other one, it'll go up here. Rather than me running around with the heater too much though, what I want to do now is what I threatened in the theory video. I'm going to measure the voltage directly between the hot pin of that other outlet and the hot pin of this outlet. Let me remove these prods. The hot pin is the narrow one. But wait, I have to change my maximum voltage setting on the meter to 500 volts. You'll see why in a minute. Because, oh, I'm shut out by the childproof lock. I'll be right back. And the power bar. And let's look at the voltage difference. The voltage difference between these two outlets is 236 volts. If I turn off the heater, the difference increases to 243 volts. So there's 240 volts nominally between these two outlets. And when I turn on the heater, I get a voltage drop of, 6 or something volts. All right. So that's what happens in terms of the voltage difference and in terms of the voltage on the other outlet. Let's try another pair of outlets. Over here, I have two outlets next to my counter. Let me turn this camera around so that we can get it. Hi again. There are the two outlets. I have stuff plugged into them. I have a coffee grinder, and I have a kettle, and I have a toaster. But let's do the test with the same equipment as before. The voltage on the right outlet is 121. The voltage on the left outlet is 121. So what happens if I plug in my heater? Well, if I plug in the heater to this outlet, the voltage falls to 117. From 121. If I plug it into this outlet, the voltage increases to 123. From 121. So this one went down by 4, and this one went up by 2. Now, something you might find interesting here is this happens even if I have a heater plugged into both devices. My kettle works fine as a heater. If I plug in my kettle and turn it on, I find that the voltage on the other outlet increases by the same amount. And the outlet that I'm plugged into decreases by a larger amount. All right. What happens if I plug in both? So I have the heater and the kettle plugged into adjacent outlets. And I'm looking at the outlet that the kettle is on. So if I turn on the kettle, it drops to 117. If I turn on the heater, it comes back to 119. So when I have a load on both the outlets, well, the voltage drop is less for both outlets than it would be if I only have the load attached to one. Turn off the kettle and the heater, and I'll pause the discussion and go back to my piece of paper. Okay, I'm back, and here we have our piece of paper. What we observed downstairs was I plugged the heater into one of the living room outlets, and that caused a voltage drop all the way through to the breaker panel. And that voltage drop on the breaker panel caused any other outlets that were connected to the black side to have a voltage drop, a small voltage drop, because there was a voltage drop on this actual black bus bar because, well, there's wires that lead to the electrical utility and coming in the house and so on, and there's a certain amount of voltage drop against that. So my outlet in the kitchen was on a different breaker, which is why we saw a fairly small voltage drop, a half volt or so. That's what happens right at the electrical panel. So what about the one that increased? Well, let's look what happened. When I plug in the load here, it causes the voltage on the black to drop, but it actually causes the voltage on the blue to come closer to the black. This moves to, they move towards one another by an equal amount. So that's why other outlets on the same side of the panel also experience a voltage drop, a small one, but still a voltage drop, because there is a drop at the actual panel. And you can verify this by going around to every outlet in your house, and you'll find they all have the same unloaded voltage. And then if you plug something in, every outlet except for the one that's on the same circuit is going to show this small change in voltage. But you say, why did one of them go up? Well, it's because it was connected to the red side of the panel. When we bring the white wire closer to the black side, we're at the same time taking it farther away from the red side. So we're increasing the voltage between the red and the neutral. And if you measured it another way, we can say the neutral is no longer at the same voltage as ground. The neutral gets moved a bit towards the black side, towards the black feed. All right, so that's what happened with the two outlets, the two wall outlets in my kitchen near the floor. What about the two outlets at my kitchen counter? Well, they had a much bigger voltage drop than you would expect just from the panel. It was a couple of volts. Well, sorry, a much bigger voltage increase because they were on different sides of the electrical supply. One was on the red side, one was on the black side, but they had a 2 volt different. You saw a 2 volt increase in one when you plugged into the other. Why is that? Well, those two outlets were wired up like this. Now, this approach to wiring is known as a split 240 volt circuit. It certainly was common, especially in kitchens, at the time my house was built in 1983. This enabled you to save wires, and it enabled you to save a little bit of electricity. Often, these two outlets would actually be in the same box. You can actually take an outlet like this. Normally, the top and bottom outlets are tied together by these metal tabs, but you can break them off. So you would often find a kitchen that had an outlet that looked like this, but you could plug your kettle into one and your toaster into the other without blowing the fuse, because one of them would be connected to the red side and the other to the black side, and they could each support 1500 watt appliances. Where if you plug two 1500 watt appliances into the same circuit, you would blow the breaker because of an overload. So that was the point of doing that. I'm not sure, they're certainly not common anymore. I'm not actually sure if the electrical code allows this form of outlet wiring anymore. And the reason is it can be a little bit dangerous. I'll talk about that in a minute. First, let me show you what happens here. So instead of splitting into red, taking just one of red or black from the fuse panel and running a separate hot and neutral, we take two circuit breakers and we tie them together. They're physically tied together so that if one of them blows, the other one will blow as well. That's an essential part of this kind of circuit. So what happens is you, instead of having a two-wire cable running from your breaker to your outlet box, you have a 3-wire plus the ground. So in some sense, a 4-wire, but it's called a 3-wire because there are 3 wires that carry actual power. You have a black, which is connected to the black side of the panel. You have a red that's connected to the red side, and then you have a single neutral. And this single neutral doesn't have to be any fatter than the other two. It never carries any more power, current, than either of the red or the black. So typically in these circuits, they were fused at 15 amps. So these were 14 gauge wire, as is used throughout my house, except for specialized heating devices. So what happens is, if I plug a load into here, well, it draws these two values, these two voltages closer together. So it brings the white wire, the neutral wire, closer to the red wire, and it brings the red wire closer to the neutral wire. But the net effect is, if you draw the neutral wire closer to the red wire, you're drawing it farther away from the black. And that's why when you plug in a load here, you get an increased voltage here. And if you plug in a load here, you get an increased voltage here. And if you plug in a load in both, they offset one another. And in fact, the electricity flows through here and almost nothing flows through the neutral wire. And in terms of energy efficiency, that's a good thing, because if you have a kettle and a toaster, the total amount of electricity that you're going to lose is half as much as if you had plugged the kettle and the toaster into completely separately wired outlets with separate neutrals. Okay, so that's the good thing. It's a handy way to save copper, and it's a handy way to save electricity. You notice the voltage drops for these heating devices are not nothing. You know, they can be several volts, so it's several percent of your total heating, or your total electricity is wasted just heating up the wires. So this reduces wastage by a half. Anyway, why is this maybe not such a good idea? If something horrible happens and your neutral wire breaks and you have a load on one of these, the other outlet will go up to 240 volts. So if you have, say, a kettle plugged in here and a coffee grinder plugged in here, and this neutral cable becomes disconnected, then you're going to get 240 volts supplied to your coffee grinder, which may well cause smoke to come out of it. For this reason, the wiring codes are actually very persnickety about what you're allowed to do in terms of running this common white cable. You just are not allowed to put junctions in it that you can disconnect without also disconnecting these outlets. Okay. Anyway, as far as I know, in modern construction, these are not used anymore, but there are lots and lots of houses built, you know, in the 60s, 70s, and 80s that have these dual tide breakers with the split circuit. And again, that's another reason, you know, why you have to have both the breakers go at the same time. Anyway, that pretty much ends the household wiring series of videos. Thank you for watching, and I've had fun doing them. It's been something that I've been wanting to do for a while, and finally I decided to stop letting production values be the enemy of getting it done. So here you go. Thank you. Bye.